Today we will discuss about ant colony optimization. This algorithm was innovated by Dr. Dorigo and it is now widely used as an optimization technique or as a programming technique of various discrete optimization problems. This algorithm cannot be used for continuous optimization problem. That means if you want to use it for a continuous problem, probability of error is very high. And also you have to just divide that continuous domain into incremental discrete domains to solve those continuous optimization problems. So let us first discuss this method or the working principle of this method with a real life example. So let us say there is a function y is equal to x square. Our goal is to minimize this function. Now the constant is x can have a value which is equals to n1 or n2 or n3 or nm. So for this case we have taken n can have 4 different values. So for example, let me take this. Let n1 is 1, n2 is 2, n3 is 3, n4 is 4. Then x can take either 1 or 2 or 3 or 4. It cannot take any value from 0 to 1 or 1 to 2 or 2 to 3 or 3 to 4, which is the case for continuous optimization problems. There the constraints are like this: x can be any value within 0 to 1. So x can take any value within 0 to 1. It can take 0.5, it can take 0.5111, it can take 0.4999 and so on. So this is not the case for our present problem. The present problem states that x can take only some definite finite values which are equals to 1, 2, 3, 4. Now let us see how to optimize it with the help of ant colony optimization. So let us first discuss about how ants search for its food. Suppose this is an ant and this is its nest. Okay. Now the ant comes out of its nest in search of food. So in one nest there can be 500, 600 millions of ants or 1 lakh or any number of ants that it can be. But mostly they are huge in numbers in a nest. So let us see whether it is black ant or red ant. Ants have the similar type of food foraging behavior. There might be some amount of change from one type of ant to other, but they are very minuscule. So what happens is, suppose this ant has come out of this house and in the search of his food. Along with this ant, there are many other ants. They have also come out of the nest, and they are also looking for the food. So I am not going to the classification of ants or any detail in their life cycle, but you can just just know that, I think all of you know that already, that in an ant nest there is one queen ant and there are few male ant and there are few army ant and there are few worker ant. Now this worker ant specially goes out for food and bring the food for not for him but for his queen. And these male ants, they have only the one purpose in their life. They are to mate with the queen ant to produce offsprings. After mating, they are dead. They die. And these army ants are used for protecting the nest. So mainly the work is done by the working ant who goes out in search of food. So they can be 5 in number, they can be hundreds in number, they can be 50,000 in number. According to the nest size, these numbers vary. So we will take just one single ant from them and say for example this ant is searching for a food and suddenly you get a food. It can be a cake, it can be any sweet object or anything. So it suddenly gets something, some food. Now as his size is very small, he cannot take this food to its nest. It can take only a very, very small parts of this food to its nest, which is of no use, keeping in view of the colony they have. So what it does is, suppose this ant has taken this path and found this food. So while going through this path, it has constantly deposited an hormone known as pheromone. This hormone is used for communication among the different members of the ant colony. Now what happens? It has deposited and goes to the, it was going through this path and suddenly it gets this food and it gets excited and it returns through the same path, remember, and always returns through a same path. So it returns to the same path and it does not only return to the same path, it also deposits greater amount of pheromones while returning. Now due to the smell of the pheromone, other ants get attracted and those ants also try to follow the same path. So these are going on. Then suddenly some ant has found this path. By view, you can say that this is the shortest path among all these 4 paths. Suppose this is the path number 1, this is path number 2, path number 3 and path number 4. Then this path is certainly the shortest path. By view you can say. But we have to prove it by ant colony optimization algorithm. So what happens? This ant takes suddenly invent this path also. So when he is going, he was depositing pheromone, but when he gets the food and returns, it can deposit greater amount of pheromone. And as this path is very short, that is why the evaporation of pheromone, look, this pheromone is a chemical material, liquid. So as is the property of many other liquids, its pheromone also evaporates. And it evaporates, how? It evaporates with the relation which is directly proportional with the length or distance covered by the ant. So when the length is much more, then it evaporates more, because when the ant is going through a path, it deposits the pheromone and it stays like that, and after a certain time it gets started to evaporate out, right? But when it is returning with the signal that it has got a food source, then it again deposits some more pheromones in a greater intensity or degree of or greater amount of the pheromone. So even if some parts of the pheromone has already evaporated out, but due to again this repeat deposition of this pheromone, this path will have good amount of pheromone to attract the other ants until this path is discovered. So basically what happens, different ant, even the same ant also take different path, because at the first time they do not know where the food is, how far the food is. So they are searching like this. So when some of the ant detect a food, it gets excited, it returns back, and while returning it deposited pheromone. And now if the path is very long, then after returning of this ant to his nest, although there are 2 times pheromones were deposited on those paths, but due to evaporation, the intensity of pheromone is less in that path, and it may be very less after a certain amount of time. So what happens if the path is very short? Then what happens is, when ant is going through this path, it is depositing pheromone. When it is returning to this path, it is depositing pheromone, and that pheromone stays for a long time because it is a very short path. So suppose it takes only 2 seconds for an ant to go from this part to this part, and then 2 seconds to return. So on total time is 4 seconds. And but due to what happened is, so not much of the pheromones get evaporated. So other ants can easily smell it or easily detect it from their antenna, and then they run towards that path, and they use that path and they again deposit pheromone. So what happens then? Then they do not prefer this route. Once they found this route, then they do not prefer this route. So no further deposition of pheromone takes place in this route. So slowly but steadily the intensity of pheromone get reduced, and after a long period of time these paths may not have any pheromone at all. So an analogy can be made with that story, that fairy tale of Hansel and Gretel. So what happened? Hansel and Gretel was, as you know, they were step parents. They have a father, but they have a stepmother. And stepmother want to get rid of those 2 children. So what happened is, one day they took those 2 children, that stepmother, and she took them to the center of the forest, core area of the forest, and she released them there, and she come back without taking the children with her. But what happened is that Hansel and Gretel, somehow they know this plan earlier. So what they have done is, they have taken that bread with them. So while going to the core area of the forest, they were tearing the breads and throwing in the path as a signal or as a marker of that path, such that they can return by detecting those markers. But what happened is, well, as they are bred, so birds or insects have already taken those bread away, so they actually cannot return. Then there is a story to end. Ultimately they kill the witch, which has entrapped them, and then they got all the jewelry of the witch, and they returned back to their village somehow with the help of their father. So that is more or less the story is. So ants do the same thing. What they do, they deposit pheromone instead of bread. And while depositing, so what happens is, look, if the bread is unattended for a long time, birds or insects will take it. If Hansel and Gretel is not returning through that path and again throwing breads in that path, then birds will take it, and no, as there will be no, what I say, as there will be no repetition of the bread throwing, so there will be no bread in that path, and the Hansel and Gretel cannot detect the bread and they cannot return to their home. So the ants, if they ignore that path, then slowly and steadily those pheromones will evaporate, and that path will be non-identifiable for any ant at a certain amount of inactivity through that path. So this is more or less the food foraging behavior of ants. Ants, all the ants, or the, sorry, not all the ants, the worker ant goes out of the nest for search of the food, and they go in different path, and if one of the ant detects some food, to signal other ants, what it does, it deposits pheromones. But while searching about the food also, they continuously deposit pheromone. But when they are returning with the information of a food source, they start to deposit greater amount of pheromone. So the path which has the solution will have more amount of pheromone due to this constant deposition of the pheromones from the to and fro journey of the ants. But once a better path is detected, a shorter path is detected, what happens? As it is short in length, the pheromone evaporation takes place or cannot be take place within that short amount of time. So greater amount of pheromone stays there, which attracts the other ant, and then they follows that path, and then they deposit the pheromones at the time they are going and at the time they are returning, and ultimately the thing is that pheromone gets constantly deposited, which rate of which is more than the rate of evaporation. So that path is discovered by the colony, and the colony comes and takes the entire food away. So that is the optimal path. So the same thing is mimicked here. So before coming into this problem, we must remember that number of domains where solution may exist is equal to number of path ant colony can take to find the food source. Previously I have said we have a function y is equal to x square, we have to minimize it, and x can take any value 1, 2, 3 and 4. And so, as this line suggests, as there are 4 solutions to this problem, that is the 4 discrete domains where the solution can be found. So let us assume that the ants are taking only, or they can take only 4 paths, 4 different paths, each depicting or indicating one solution as given by this. If there are 5 domains, 5 discrete domains, N1, N2, N3, N4, N5, then you will consider 5 different paths. If there are 6 domains, 6 different paths. If there are 10 domains, 10 different paths. Please note that, because don't confuse with the number of ants. Number of ants is something different with the number of paths. Number of paths is equals to the number of domains where the solution is allowed for that optimization problem. It is not, those solutions are not ants are not the solution. Okay, so Number of ants, we can take any number. Randomly, we can take 5 ants, we can take 50 ants, we can take 100 ants. It is up to you. So 5 ants means 5 repetition in one iteration. 50 ants means 50 repetition in one iteration, and so on. Suddenly more the ant, greater and chance of detecting the good solution, reliable solution. But computational time will be larger, longer. But when there is shorter number of ants, then the solution will be less reliable, I agree. But it will be faster convergence. We can expect a fast convergence, and computational capacity will be required computational capacity will be minimum. So it is always good to take a trade-off can be done, and generally it seems that 5 ant is enough to detect a solution which is reliable. So what is the note? I have discussed the first note. Second note is each path has its own probability of selection, indicated by the amount of pheromone deposited. That I have discussed. More pheromone is more prone to be selected. At the beginning of the iteration process, however, each path will have equal probability of selection, just like a Rowlett wheel. That I am coming later on. So what I mean is, so there are 4 discrete domains for this problem. So we have 4 different paths through which that ant can get a solution. So what I mean is, now our job is to select the best path or shortest path possible for that ant to get the food. And this can be detected with the help of 3 formulas. First is this probability of path selection, Pij. I is the starting path or starting node. J or starting path, I will say. No, starting node, it is good. I. Okay. So, and J indicates the number of path. So, if this is the I, this is the I. So, these 4 paths are J's. Okay, J is equal to 1 means this one, J is equal to 2 means this one, J is equal to 3 means this one, and J4. J is equal to 4 means this path. Now this tau is, tau depicts the amount of pheromone which was deposited when the ant is traveling from I to J. J can be any path, whether I to 1, I to the food source through J is equal to 1, J is equal to 2, J is equal to 3, J is equal to 4. So basically what happens is that ant can take any one of the 4 paths, uniform probability. So at the initial time. Now what happens is, so this tau is the amount of pheromone deposited. Here you see tau, amount of pheromone deposited in the path, and divided by the total amount of pheromone deposited among all the path. That means if one unit pheromone is deposited for this path, 1 unit deposited for this path, 1 unit deposited in this path, 1 unit deposited in this path, then total amount of pheromone deposited in all the 4 paths is 4. So probability of path selection will be 1 by 4, 0.2. So that is what it is. At the initial stage, we assume that all 4 paths has equal amount of pheromone. So probability of path selection will be equal as well at the time the iteration is starting. 0.25, 0.25, 0.25, 0.25 as I have detected, as I have calculated. So what is the case of Rowlett wheel now? I will come back to that later on. Before that, I want to say, what is the amount of new pheromone, how it is determined? So first we are determining the amount of pheromone and probability of path selection by this equation. Equation A. Second is equation B, by which the amount of new pheromone is determined. So the amount of new pheromone is determined by 1 minus rho into old pheromone plus summation of change in pheromones in all the path. Not all the path, sorry. Change in pheromone in single path. But why this is summation? Because not one ant has not traversed the path. If you are considering 5 ant to be there, then 5 ant has traversed that path and has changed the pheromone accordingly. Because if one ant is going and depositing 2 units of pheromone, then second ant is come, it has deposited 3, so total amount of pheromone will be 5. So as there are 5 ant depositing different amount of pheromone, then you have to add all those pheromones to depict the change in pheromone amount. Clear? But in that single path, not different path. Okay, because this tau ij is same for all the different ants. Okay. Now what is rho? Rho is actually rate of evaporation or rate of pheromone evaporation. I have already discussed about the role of evaporation here. Rate of pheromone evaporation. Of course, this depends upon time, but initially we take it as 0.5, or sometimes it is assumed that constant rate is 0.5. Okay, so 1 minus rho tau, this is the old value of tau. That means the old amount of pheromone. In this case, if this is the second iteration and this is the first iteration, then the amount is 1 unit. Right, so 1 minus 0.5 multiplied by 1 plus the change in pheromone. How it is calculated, change in pheromone? It is calculated by this formula, Q equals to F best by F worst. So what happened is, in the initial or the previous iteration, some value of the function fx you will get. Okay, so among all the previous iteration, if that value is the best, then write that value here in the numerator, and among all the previous iteration, when the function has the worst value, write it in the denominator. As this is the minimization function, then when the function value is very low, very minimum, then it is best. So exact, write the exact value to this one, numerator. And when it is very high, so it is highest rather, then you write that value, that highest value to denominator. So just identify this term function. This is not the value of x for which function is based. It is the function itself. And q is any constant which is generally assumed to be 2. Q is a constant which is generally assumed to be 2. So that is the del Tj for 1 ant. For 5 ant, all these del Tj will be added, and ultimately it is added to this expression. Ultimately this del T for all ant is added, and then it is again added to this 1 minus rho multiplied by amount of pheromone tau of the previous iteration for that path, for that same path. Remember, this tau nu is for one path only, ij. It is not for all the path. You have to calculate it for different path. Okay, so now let us take the example of Rowlett. So let us recapitulate until now what we have discussed. So the problem is like this: y is equal to fx is equal to x square. This is the objective equation, all of us know. And x can take any value 1 or 2 or 3 or 4, but no value in between 1 or 2, in between 2 or 3, in between 3 and 4. That is already discussed, because these ant colony optimization is for discrete optimization problem. And discrete means when the domain is discrete, like this. Now, as I have told that number of paths will be determined by the number of discrete domain available to that problem. So this will be given to you as a constant definition, subject to x belongs to only n1 into nm. So here n1 is 1, n2 is 2, n3 is 3, n4 is 4, that is clear. And so there are 4 different paths. This is why n1, n2, n3, n4. Now let us at the beginning what I have said. Each of the path will have same amount of pheromone. So to explain it, let us take the example of roulette wheel. Roulette wheel can be found in casino, where what happens, a plastic ball is thrown to a rotating roulette wheel. This is the roulette wheel. And the operator rotates this roulette wheel at a specific speed. When that roulette wheel gets that specific speed, it releases the ball, plastic ball, a very small ping pong like ball, into that rotating roulette wheel, and if that ball can fall any of the chamber as indicated here, any of the chamber. Okay, and there are numbers written here, all this cycle 1 to I think 100, the number is there. So there are 8 chambers, so probability of this ball to fall into one specific chamber is 100 divided by 8. Because there are 8 cap pockets, so it can fall, this ball can fall any one of these 8 packets at the initial time, as per the initial iteration of the ant colony. Not real life roulette problem, but at first it said that that when I release the ball into a rotating roulette wheel, the probability that ball will fall in a specific packet is equal. And as there are 100 numbers written here, if there are 32 numbers written here, then 4 numbers per packet. If there are 100 numbers written there, then you can say how much? I think nearly 12.5 numbers in each packet. So those 12.5 numbers can be, that ball can touch any of those 12.5 numbers at every rotation. Okay, so that is for roulette wheel. But in case of ant colony, what happens? At the initial iteration, it is equally divided. A roulette wheel, which is divided here, the 4 number of path is there, so it is divided into 4 different paths, and your probability is equal. That means the ball can fall into any one of these packets or pockets during rotation. But if what happens is, in the second iteration, the probability of all the paths will not be same. Some will be higher, some will be lower, and accordingly the path size will also change. But sorry, not path size, the packet size will also change. So here it is same, right? If this is A1, if this is A2, if this is A3, if this is A4, then A1 is equals to A2 is equals to A3 is equals to A4. But whenever the packet size changes from the second iteration, so is it A1, A2, A3, A4 is same? No, A4 is very high, very large compared to all this A1, A2, A3. So the chance of the ball falling into this packet is maximum, naturally. So this energy was applied for this ant colony optimization also. Initially what happens? Each of these 4 paths has the same probability. So, or the rather same amount of pheromone, 1 unit, 1 unit, 1 unit, 1 unit. So what happens? Each path will have a probability of 0.25, because this is the equation suggests. 1, this is the amount of pheromone in the path ij. Always remember I indicates the location of the ant, j indicates the location of the path. Okay, so there will be this P11, P12, P13, P14, all will be equal at the first iteration, right? P11 means the probability of this path, P12 means the probability of this path, P13 means this path, P14 means this path. मतलब N1, N2, N3. Now come to the main part. So before beginning of this solution, we will assume how many number of ants to be used. So if I assume that 5 number of ants to be used, then what happens is, then you have to generate now 5 different random numbers. How will you generate? In case of continuous optimization problem, the domain was continuous, Ax can be within 0 to 1, so any value you can take within 0 to 1. But this is not the case for this discrete problem. There are 4 different domains. So that is why what happens is, at the initial iteration, as there are equal probabilities for all the paths, so what we do is, we try to generate something like we create a area like 0 to 0.25, 0.26 to 0.5, 0.51 to 0.75, and 0.76 to 1. So these are the 4 division we have made. So 0 to 0.25 is representing N1, the first domain of the discrete domain. 0.26 to 0.5 is representing N2. 0.5 to 0.75 N3. 0.76 to 1 is N4. Okay. Next step, in the next step what happens is, as there are 5 different ants, we randomly generate 5 different random numbers. And this random number generator will follow the uniform normal distribution pattern and will generate any value within 0 to 1. So basically that random function of Excel, rand 0, 1. And now is the main interesting point is there. So we have created representative domains for this N1, N2, N3 and N4. Now what happens for 5 different ant, there are 5 random numbers. So what are those random numbers? Suppose R1, this is for the ant number 1, the random number generated is 0.27. R2 is 0.34. R3 is 0.5, R4 is 0.7, R5 is suppose 0.85, right? So there are 5 ants, 5 random number to be generated, and these are the random numbers: 0.27, 34, 5, 7, 8.5, 0.85. Now you see. Take the first one, R1. This is the first ant, 0.27. Which domain it is falling? This domain it is falling, 0.26 to 0.5. So it is N2, it is falling, correct? So N2 is, for our case, it is 2. So N2 is 2 means X is 2. And as the equation is y is equal to x square, so y equals to function of x will be 4. And then the random number 2, if you take 0.34, where it is coming? N2, 0.26 to 0.5, N2, so N2 is again 2, So next ant will be 4, right? 2 square 4. And then you see 0.51 to 0.75, sorry, the random number is 0.5, and this is also N2 because N3 start from 0.51. So this will become 4 also. Then ant number 4, it is 0. I think 4 it is given, or what? No, it is 0.7. Sorry, it is 0.7 it is given. So 0.7 means it falls in the third domain in 3, which is 3 in our case. So put x is equal to 3, so it will become 9. The function value will become 9, correct? And then take the value of the R5, it is 0.85, so it falls under the 0.76 to 0.1. 0.85 is falling into 0.76 to 81. So it will be equals to N4. N4 is here 4. So X is 4. So Y is 4 square 16. So the fifth ant will have a value of 16. So at the end of the first iteration, what happened? Y have 5 values: 4, 4, 4, 9, 16. So within these 5 values, which are the minimum value? These 3. Our problem is about minimization. So these 3/4 is the ideal solution after iteration 1. So these 3 is a best. This 16 is the first because it is the maximum value. I think this is the maximum 16 because 4, 4, 4, 9, 16. So the maximum is 16. So this will be the worst. This is the situation for the Y1 first iteration. Okay. Now what happens? So this is the first iteration. Now come to the second iteration. Now again 5 values will be generated for 5 ant randomly. So this first one was for the first iteration. So let it name it as R11, R12, R13, 14, 15. And so this R1, these are resulted into Y1. And so this is the optimal point, or the minimum is 4 and maximum was 16. So now what we will do first is to find out the new tau, because the pheromone probability or pheromone amount has changed. Now probability will change, but filal or now presently pheromone amount will be changed. So what is the amount of pheromone for this new iteration? Correct? So it will be find out by this formula, equation B. What is this formula? 1 minus rho multiplied by the old pheromone plus summation of del T. That is, summation of del T means here 5 ant is there. So 5 ant has deposited 5 times different amount of pheromones. So all the summation of those all pheromones will be given here. Okay, so ultimately how it will be given I am coming, but let us calculate this equation now. So tau nu, so this will be the tau ij nu, because tau is now different for different path. Okay, so what is that? That we are calculating. So let us see, this tau is 1, 1. What happens in the 1, 1? So the formula is like this: 1 minus rho multiplied by the old tau, tau 1, 1 old, and plus del tau ij, or this is 1, 1 summation, because of the 5 different and 5 different you will come. Okay, so rho we have already said it is 0.5. So what will happen? 1 minus 0.5 into tau was 1. Previous iteration, initial iteration, all tau is same. Plus the formula for del T was Q multiplied by F best by F worst. Correct? So what happened? Q is 2. I have already discussed. 2 into F best was 4. F west was 16. Okay, so this becomes 0.5 plus 2 into, I think 2 into 4 by 6 has become 4182. So 2 into 4 by 16 will ultimately become 0.5 plus what is it? It is 0.5 again, correct? Half is 0.5. So the new tau is again 1. But for this part, correct? For the first part. So as the old pheromone was same, evaporation rate was same. So what happened is this 1 will be same, and let us say what will happen is basically this 0.5 can be directly multiplied by 4, so it become 2. So ultimately this will be 2.5. Correct, because you see this what happened is 1 minus rho into tau old. So tau old is 1 for all the path, whether it is the first path, second path, third path, fourth path. For all these 4 paths, the tau old is 1. 1 minus rho is same, 0.5. And this del tau will also be same, 4 by 16 and these things. So, so for this del tau, what happens is del tau you can multiply 4 into del tau, right? So straight away, because this del tau will be same for each of the path. So this will become, as del tau is coming to what? Del tau is coming to 0.5. So because this is Q, 4 by 16, so let us say 1 by 4. 4 ones are 4, 4 is 16. Now 2 ones are 2, 2 is 4. Half means 0.5 into 4, because summation of del t tau. So 4 into 0.5 is 2.5. Sorry, 4 into 0.5 is 2, and there is already one 0.5 here. So resultant will be 2.5. This will be the new amount of pheromone, right? So accordingly, now what we will do is we will calculate the probability of 1 1, probability of 1 2, probability of 1 3, probability of 1 4. 4 path, 4 probability with the same equation that we have followed, but this time the taus will be somehow different, not same. Now you will say how it is not different, because here it is, what we are seeing is, here it is same as we can see. So the procedure, if you look into this procedure of this ant colony optimization, what is happening is that that randomization or random number, 5 different ant is following. Correct. So based on that random number, we are getting some new that discrete domain, and accordingly we are assigning the values to the x, and finding the values of y. So for 4 different domains or different solutions, we are getting 4 different y's. Not for 5 different, and so 5 times we are assigning values to x, and 5 different y's we are getting, among which we are finding the minimum value. That becomes a best, and the worst value, the maximum value, that becomes the a first. And for finding the new tau, we are using this formula 1 minus rho multiplied by tau, old tau, plus summation of del taus. Summation of del tau means 5 ant has traversed the path. So for each ant there will be a certain amount of pheromones. So for each ant there will be a pheromone, new pheromone. So those are added. So but initial iteration the amount of pheromone is to be same. That is why straight away you can multiply 5 into the value of delta. Okay. Now let us come. There is some mistake. So this is what happened is. This is for a path. Let us do this part another time. Let us do this part or repeat this part. Okay, because I want to show something here. So it must be so let us see now. Let us begin from the beginning. So what happened is, what I will not repeat it again. So our problem is now the new tau, right? Now there can be some cases. Look, after the first iteration, we have one path which is best, one path which is worst, and remaining 2 paths neither best nor worst, right? NB, NW1, NB, NW2. Now it is assumed that at the best path there will be no evaporation. At the best path there will be no evaporation, only deposition. But the worst path or the other path, there will be, but for the worst path, what will happen? There will be no deposition. Of pheromones. So that the worst path become worst and the best path remain as best. Right? So that is why what happened is, for the best path, when we are calculating tau nu, for the best path, we will change this equation 1 minus rho multiplied by tau old plus del tau summation. So this we will change. How we will change? 1 minus rho. There will be what I said, no evaporation for the best path. So no evaporation means this rho becomes 0. So this what will happen? 1 minus 0. First time tau was 1, right? Plus our delta. And delta was, as we know, is 4 by 16 because F best was 4, F worst was 16. right? So this is for the tau best, the tau for the best path, and similarly we will calculate a tau nu for the worst path. So where that happens, where evaporation happens, right? But deposition doesn't happen. So del tau is 0. So 1 minus rho means 1 minus 0.5. Multiply for the first iteration was 1. So 0.5 into 1, this will become 0.5. Okay, right? So, okay, so now for the other part, NB, NW1, NB, NW2, what will happen? The entire equation will stay. 1 minus rho multiplied by tau volt plus del tau summation. This summation is for the ants. We have 1 to 5 ants, so 5 different terms. So 1 minus rho, this is for nu tau when it is neither best neither worst. So this will be your 1 minus 0.5 multiplied by 1 plus, I think, in our case 2, I think, correct? So for all cases the delta will be 0.5 for all the 5 ants. So sorry, not 2 but 2.5. Okay, so this you can calculate. So once you got the tau now you will just go for again calculate P for the best. P means probability of pheromone. P for the best, P for the worst, P for NB neither best neither worst 1, P for neither best neither worst 2. This probability, and remember this time tau will be different for different path. So summation of tau will not result into 4 but some different constant. Isn't it true? Because this tau for best is something else. This is, I think, will be what? 1 minus 0 is 1 into tau is 1. Del tau is actually this 2 into 4 by 16. So it becomes 2 into 1 by 4. Then 1 half. So this becomes 0.5. There are 5 ants. So we will multiply 0.5 with 5. It becomes 2.5. So this term becomes 2.5. So ultimately the new tau will be 3.5. So for P based, probability of pheromones for the best path will be 3.5. Similarly for worst path, though 1 minus rho, there will be no deposition, so del T is 0. So 1 minus rho into tau, so 1 minus 0.5 into 1, 0.5 into 1, 0.5. So here the tau will be 0.5. We are coming into the summation. Now for NV and W1, what happened? This one. So 1 minus 0.5 into 1, and these will be our 2.5, correct? So these will be our 0.5 plus 2.5, this will be 3. Isn't it so? So for both these cases, NB W1 and W2, these will be 3, these will be 3. So total tau, summation of tau will be 3.5 plus 0.5, 4, 7, 10. So this summation of all tau will be 10 this time. Then you have to calculate, this becomes 0.7, this becomes 2, then you calculate and accordingly something will be there. And you will repeat the same process as you have done earlier, but here is a catch. Now what happens is, let us say this 3.5 by 10, correct? So let me calculate it. So let me calculate it a little bit, such that so first one was, I found that 3.5 by 10. So 3.5 divided 10. So it is coming as P based probability of pheromone deposition for the best path of the previous iteration is coming to be 0.5. Sorry, 0.35. It is coming to be 0.35. For the worst path, it is coming to be, it is this tau nu was 0.5. So 0.5 divided by 10, it is coming to be 0.05. Then for the remaining two is 3 by 10, 3 by 10. So 3 by 10 will be 0.3. So this time this will be 0.3, this will be 0.3. So now you see another thing you have to know is that so P based is 0.35, P worst was 0.05, P NB NW 1 and 2 is 0.30, 0.30, correct? Now to find the percentage ratio of each of the path into that old roulette wheel, now these will be 35%, these will be 5%, these will be 30%, these will be 30%, correct? Just multiply 100 with them, right? So now the base path is carrying 35% to so the base path is carrying 35%. So that will be, this will be 30%, not to scale please, and this is 5%. Okay, so how we will divide the domain 0 to 1 now that we have used before generating the random numbers. Now it becomes 0 to 1. Earlier all are equal, so we have divided this 0 to 1 like 0 to 0.25, 0.262, 0.5, 0.512, 75, 762, 1. Now what we'll do, how we will divide this 0 to 1? First part is 35%, so 0 to 0.35. Second part is only 5%, so 0.362, 0.40. Then next is 30-30, so 0.412, 0.7, 0.712, 1. Then the next is we have 5 ends, so again you generate R1, random number R1, R2, R3, R4, R5. And suppose this is R1 0.3, R2 is 0.5, R3 is 0.7, R4 is 0.8, R5 is 0.9. Now what will happen? For R1 0.3, it is falling into this first division, this one 0 to 0.35. So you move to N1, right? So that is the way it will work. N1, now N1 becomes that 0.0 to 0.35 if N1 is the best path, correct? So best path can be detected from the previous iteration. So if N1 is the best path, how will we detect it from the previous iteration? The probability after the completion of the iteration. So let it see. So N1, so if 0.31 is N1, 0.3 is the random value generated, so these will become N1. Similarly 0.5 is coming into the third point, so 0.5 is actually N3, 0.7 is actually N3, 0.8 is actually N4. Yeah, actually N4, 0.9 is also N4. Correct? So we have that values of N1. Now put it as X, again X, again X, again X, again X. So 5 different X, 5 different Y. Again you compare and you find the best function, worst function. And then again you try to find the new term value. For the best path, for the worst path, for the not best, not worst, not best, not worst path. So this is in short is the what we say as the ant colony optimization. Ultimately what will happen? All the 5 ants will have the same value or will generate the same value for the function. At that one, that means what? For F1, F2, F3, F4, F5, this all F's for that ant number 1 and number 2 and number 3 and number 4 and number 5, they will generate function 1, function 2, function 3, function 4, function 5. This will be, all will be equal. At that moment, you have to stop your iterations. Okay, at that moment, you have to stop your iteration because there will be no further improvement. Okay, so this is overall this ant colony optimization problem. I solve it with a working example. So go through the problem repeatedly because it is a little bit confusing with path and number of ant. Remember, number of discrete domain equals to the number of path, and number of ant can be anything that you wish. But yes, more the number of ant, more reliable will be the output. Lesser the number of ant, less reliable will be the output, but there will be a first convergence and also requirement of computational capacity will be less. So that is what we have to say. Thank you for now. If you like this tutorial, like the video or subscribe. Okay. So finishing for now.